In this presentation, I want to talk about dispersive fade margin and its effect on radio link availability. I'll start, however, by introducing myself. My name is Rod Walker. I have an electrical engineering degree from McGill University in Montreal. I've worked 27 years as a microwave system designer, engineer, primarily with a major telecommunications equipment manufacturer, designing customer microwave systems and working with equipment designers and with manufacturing. Subsequently, I started a 17-year career to date as a consultant slash contractor, providing microwave system engineering design support and developing customized software applications primarily for microwave system design. In this talk, we'll look at the following points. So what is dispersive fading? Why is it important? Under what conditions can it cause problems? How are radios characterized in their tolerance to this effect? How is this effect included in calculating link performance? And what is the dispersive fade occurrence factor? In this next slide, I show you a simple example of a transmitting antenna at the bottom left, sending a signal across to the receiving antenna on the right. That's the direct wanted signal in the center. And I also show you some signals, indirect signals that get to the receiving antenna from the same transmitter, so essentially the same signal, but following longer paths through scattering or reflection, and reflection can be within the atmosphere. So the result is that the receiving antenna receives multiple signals, and each of these signals is different in delay, the shortest one being the direct one generally, and the paths that go off through scattering and through reflection also tend to be weaker because they've suffered reflection losses, scattering losses. So the receiving antenna receives all these multiple signals, varying delays and varying amplitudes. And what this does is it causes a distortion of the received signal, its spectral shape, and that causes issues in availability, sometimes in dribbling errors, and it can even, if it's bad enough, it can cause complete outage of a link. In this next chart, I show you a plot of a QAM spectrum within a channel bandwidth. That's the blue line. And this is a typical simplistic plot, but it's very much close to reality. The red line is the red notch, rather. It's called a dispersive notch pattern. And that happens when these delayed signals of the same signal source are added into the wanted signal with different phases, and they cause this kind of a notch effect. Of course, the depth of the notch and the exact position of the notch and the width of the notch are all dependent upon the actual conditions, basically the strength of the reflections, the delay of the reflections. Now, if these notches are narrow enough, and that can happen with fairly long delay reflections, they may actually not take much of the energy away from the RSL signal. So the RSL might actually look, very close to what it should be. And if you're not looking at a spectrum analyzer, you may never actually see the notch or be aware of it, and it'll look like a mostly unfaded link. So under what conditions can this notch, cause problems? This is very much dependent upon the link, of course, but the primary factor is the link band. If you operate in higher bands above 11 gigahertz, availability is dominated by rain outage generally, unless you're in a very dry environment, like a desert, for example. But as a general rule, above 11 gigahertz, rain outage dominates by far in availability calculations, and multipath and dispersive effects are really so weak compared to the rain outage that they're not important. So as a general rule, we look at dispersive fade problems below and including 11 gigahertz plans. The second item that's really a contributing factor is the path length. So the shorter the path, the shorter the time difference between the wanted and delayed signals. And if you look at the notch plots, and I'll show you a couple in a moment, what happens is as the delay gets shorter, the notch gets wider and wider, and it looks more and more like a flat fade. And that's of course related to the channel bandwidth, which is the next point. The narrower the channel bandwidth, the less than a notch can look like a notch in your channel. It might just look more like a flat fade. And indeed, in the past, before dispersive fading was characterized and included in availability calculations, very often in those cases, the dispersive notch just was treated as part of the flat fading. In this next slide, I have a table at the top where I show the path for different path lengths and different reflection distances, what the delays are between the two signals, and I'm only using a two-signal model in this analysis. And if we have a strong reflection, essentially no loss, which is not really reality most of the time, but it's very illustrative here. If we have a strong reflection, I can characterize how deep the notch is and how wide it is. So I'm showing in this table here on the first line a case where the notch width at a depth of 20 dB from the normal received signal level is 20 megahertz wide, which is pretty wide. Now you'll see this delay difference 6.3 on this first line. This is the standard that was agreed upon years ago for determining availability as a result of notch or dispersive fading outages. So I've created this first line as an example of that and plotted it. I'll show you in a second. But essentially for the 30-kilometer link with a reflection at 337 meters off the path, we end up getting this delay difference of 6.3, and the notch with a 20 dB depth as it goes down is 20 megahertz wide. Now, I have other cases here. I ran a number of cases just to get a handle on some numbers, and for varying path lengths, reduced path lengths, you can see that the delay difference gets smaller and smaller very quickly, and as a result, the notch width gets wider and wider. This is just basically calculating from the geometry of the path. Now, at the bottom here, I have two plots. One on the left actually has two notches in it, but we'll talk first about the deep one. It's this black line that goes down. This is one where we're assuming a perfect reflection, so we have a delayed signal coming in with roughly the same strength as the main signal, which, as I say, is not generally the case unless you have strong reflections off water. But this is what happens as you get this notch, and you can see the characteristic width. I'm looking at minus 20 dB from the RSL. The width of the notch is 22 megahertz wide. Now this particular plot and the next one I'm going to talk about in a second here, they were all calculated using the standard 6.3 nanosecond delay, and I'll explain a little more in a second where that came from and what it's about. Now the other red line here is also a notch, although it's so shallow it doesn't look like a notch, and that's because the reflection signal is so weak. Basically there was such a high reflection loss that we didn't get any depth of notch in it, but it's very illustrative of how important the reflection loss is for the delayed signal. The dashed line here is a channel bandwidth of 30 megahertz. I used that because I was working with 6 gigahertz case when I did this plot. So basically the channel bandwidth is very close to 30 megahertz, and it's shown here. Now I should point out, of course, that this pattern is pretty much band independent. The width of the notches and the channels and so on is related much more to the time delays and the reflection losses, and it's not affected by the actual band. The chart on the right here, I basically did the same thing for one of them, but I used a 15 nanosecond delay just so we could see the difference. The depth is pretty much the same, as makes sense, but the notch width at the same minus 20 dB depth is now 9 megahertz, whereas previously it was 22. So the next question is, how are radios characterized in their tolerance to this effect? So radios have a parameter which is called dispersive fade margin, which is used in link availability calculations, and basically that characterizes the tolerance to dispersive fading. So the image down here shows an example. This is taken from path loss for an iPasso radio. I brought up the radio spec, and you can see the dispersive fade margin in decibels as a parameter of the two thresholds, 10 to the minus 6 and 10 to the minus 3. Generally, we work with 10 to the minus 6, so we're looking at minus 31. Now, this is a number that the manufacturer has given as a part of a specification of their radio, and it's based upon the 6.3 nanosecond standard that I mentioned. So 6.3 nanoseconds was set years ago as a result of studies done by C.W. Lundgren and W.D. Rumler, and I give you the reference at the bottom of the slide here. They did a lot of testing, looked at dispersive notches and reflection delays, and came up in their testing with an average number, standard number of 6.3 nanoseconds. At the time, these were for long-haul radio links, which was pretty common for long-distance telecommunication, and it became a standard. So radio manufacturers who publish dispersive fade margins use this 6.3 nanoseconds, and is as a result used in availability calculations. Of course, in paths where the reflections are different delays other than 6.3 nanoseconds, the calculations, of course, are not going to be perfect, but it is a standard, and it's included as part of the availability calculation. So how do we include this effect in calculating link performance? So generally, when we do availability calculations, we plug a fade margin number in, and that gives us our outages and availability. If we include a dispersive fade margin as part of our calculation, we essentially adjust that flat fade margin number, and we create what's called an effective fade margin. So we use this formula that I'm showing here to add the flat fade margin effect with the dispersive fade margin effect. We calculate this effective fade margin, and then that gets used in the calculation of availability. You'll notice the negative signs are important, but also this FOC, which is a fade occurrence factor. When the formulas were being developed, the people who developed them looked at a lot of different paths and different conditions, and realized, of course, that the effect of dispersive fading is very different from the effect of fade margin. So they put in what essentially I call a fudge factor, this fade occurrence factor. And at the bottom of my chart here, I give you typical values that are recommended to use for that factor when you're doing this calculation. So for good propagation conditions, the number they say should be between 0.5 and 1. For average conditions, 3. For difficult conditions, 5 to 7. And for extremely difficult propagation conditions, 9. You can go and read about what good, average, difficult, and extremely difficult are, but essentially these are the numbers that you would plug into this effective fade margin formula, which then would end up in your availability calculation. I also note at the bottom that some manufacturers suggest a value to use for this FOC factor. Notably, Nortel years ago advised 5.0 for non-space diversity paths, and they provided a formula to use to figure that out for space diversity links. So lastly, I'm showing a screen here from Path Loss, and other softwares will have similar screens where the dispersive fade occurrence factor can be entered, and in this example it's shown as 1. There's a blue button here on the right, blue arrow. In Path Loss, if you click on this button, the software will work out what it thinks that factor should be. It does that by looking at the entered terrain information for the link in question, but you can put in whatever number you want. So that concludes my discussion of dispersive fading and how it's included in availability. I hope this was useful. Thank you.